Great. Well, I'm real happy. Thank you very much for those kind words. Thank you, Rector and Martin and Yasha, for inviting me here to Ankara. It's my first visit to Ankara, not my first visit to Turkey, and I'm delighted to be here, and I obviously need to spend more time. So, what I'd like to do today is tell you something about how the world of science is changing and what the implications will be for both scientists, computer scientists, and for university libraries, in my view. So, the topics I'm going to cover are, say, something about the data deluge and the fourth paradigm. I'll give some examples of that, and before I then talk about the whole of the data life cycle, from taking data to finally publishing and archiving. I do want to say something about the role of research libraries in universities and repositories for research information. Open data and open science, I think, are extremely important in the world. We need to solve some of the problems facing the world in environment, in healthcare, epidemics and disease, and I believe computer science and science can actually help make progress on these for the world. And I'll end with just three topics: clouds, search, and what I call semantic computing, which is about how we deal with this information deluge mentioned by the rector in terms of books. I think I read probably a book a week, so it's about 50 books a year. If I live to 100, that's about 5,000 books in my lifetime. Not very many, but it's a very interesting challenge. So, data deluge. So, I think we're seeing around us a tidal wave of scientific data, and these are just some of the articles lately pointing out the fact that science is being changed, industry is being changed also by the amount of data. And what we need to have are technologies and tools which enable us to find subtle, small signals in all this mass of data. How can you find the significant information in a whole sea of data? And that's the topic of this talk. Just to show you that this is not just an academic exercise for research scientists, I looked in, I'm not allowed to use Google, so I use Bing, right? But I put in Bing data scientist, and this is what comes up. The data scientist is the role of the future, the hottest job you haven't heard of, the hot new gig in tech, data scientist, mine, visualize and learn. So the students that you train in data science will be employable by industry, by retail industry, by the advertising industry, by many industries, financial industry and so on, will want people who have the ability to mine and sift and find signals in huge amounts of data. And so, in the US, there's a movement which is combining sort of library schools with information science, and they call it the iSchool movement. And this is an example of one of the iSchools in the US at Syracuse, and they're now offering a new graduate course in data science, so that you can go and get a diploma in data science, which they believe makes you very employable. So, fourth paradigm in e-science. This is a slide from my colleague Jim Gray. Jim Gray was a Turing Award winner in Microsoft Research, and unfortunately he disappeared at sea 4 years ago, and is no longer with us. But he gave, 2 weeks before he disappeared at sea, he gave a talk about what he called the fourth paradigm. This is one of the slides. I'll use 3 of his slides. So he was pointing out that fields like biology or like chemistry have developed 2 subfields. One is computational biology or computational chemistry, when you're using a computer to simulate a molecule, to how a molecule works and how it folds in a protein or whatever. But in addition, they're developing what he called ex-info, bioinformatics, chemoinformatics, where you're having to deal with all the huge amounts of data, and it isn't computing in a traditional sense of simulating something, it's actually mining huge amounts of data. And the problem he illustrated here, you have data coming from experiments and instruments, you have archives, you have together to get questions and answers, and to find out significant results that can solve your problem. And the scientist, instead of having just to program a computer, needs to handle large amounts of data, much larger than they've had in the past. How you organize it, do you use a relational database, what's a schema, how you reorganize it, how would you share it, how you visualize it, how you mine it. These are different skills that we haven't had scientists to have in the past. These are the skills they need to succeed in the future. So, Jim Gray then talked about the emergence of a fourth paradigm. What did he mean by that? Well, traditionally, since the days of the Egyptians and the Greeks and so on, we've done experiments on nature, made observations and taken data. A few hundred years ago, people like Isaac Newton and Robert Maxwell formulated a lot of those experimental data in laws of science. Newton's laws, Maxwell's equations, now we have in quantum mechanics the Schrödinger equation, of course, and many others. And from that, there are now two ways to explore science. One, you can go and do an experiment. Secondly, you can actually mathematically explore the implications of these equations for a particular situation. And then you can make a prediction which you can go and test. And this has traditionally been the two paradigms, the two pillars on which scientific research has been done over the last few hundred years. But in the last century, in about the 1950s, we developed digital computers, and they enable us to investigate nature in a new way. If you want to investigate climate change, well, we only have one climate. It's difficult to do experiments. But with a computer simulation, you can simulate different conditions. You can investigate the potential for global warming and so on. Similarly, if you're trying to understand how the galaxies were formed, galaxy formation, you cannot do experiments, and the equations are far too complex to solve analytically, but you can do simulations on a computer. So Ken Wilson, the Nobel Prize winner in the 1970s for particle physics, called computational science the third paradigm. And what you need to teach your students for that? They need to know about numerical methods, they need to know about algorithms, they need to know about parallel computers, architectures, and parallel programming. A whole different set of skills than traditional skills of experiment and theory. And that's what Ken Wilson meant by the third paradigm. What Jim Gray observed, that nowadays we're seeing a new type of scientist emerge who needs different skills from all the three previously. And he called this data-intensive science. We're being overwhelmed by science by all different sources, instruments, simulations, sensor networks, and I'll give some examples in a moment. And what we need to do is to make sense of that and find significant results that will actually help us understand the world around us. And these are the tools that I ran the UK e-science program for 5 years before joining Microsoft Research. And it was about science which is often multidisciplinary, it's collaborative, it may involve people in different organizations, and for that you need tools to enable them to collaborate, to examine the data, to mine it, to put them together, to share, to interoperate and so on, and to visualize and explore the data. And these are, if you like, the e-science tools that we're developing now. I hope in 5 years' time or so, they won't be called e-science anymore. It'll just be the way we do science. But we'll have these tools and technologies. But now is a very exciting time because we can take a part in developing these technologies. So we're seeing, as I said, the changing nature of scientific discovery. Complex models which are too difficult to solve analytically. They're often multidisciplinary. If you're in a pharmaceutical or a drug company, you have a group of biologists. They need to talk to a group of chemists. They need to talk to some geneticists. Now, they may be in different buildings, but they may be in different towns or even different continents. And you need to enable these groups of scientists to work to solve a problem together. Data from sensor networks is real time. It streams in very quickly. You have to make decisions. You need tools and technologies to help you do that. And as I said, distributed organizations, virtual organizations are not sure I like the view of the world entirely put forward by your rector when everything is virtual, because it's actually nice to come to a place like Ankara and meet people face to face. But I do agree there will be increasing need for tools to support distributed virtual interactions. And these are the sort of challenges that are facing science and indeed industry today. And in the fourth paradigm, this is the book here, there was a series of essays. My role as chief editor was to help get the authors there, and there was a computer scientist and a scientist. And my role was to make them not write a scientific paper, but an essay which would be readable by a much larger audience. So the hope is that these are visions of the future in the environment and in healthcare and in cyber infrastructure, the infrastructure you need to make that happen. People looking ahead 5 years, 10 years down the line to see how things will change. So they're an interesting collection of essays, not definitive, but they're certainly not a Microsoft view, but they're a view of how the scientists and computer scientists see the world. And in addition, there's a fourth section on scholarly communication. This was put together by my colleague Lee Dirks, who alas died a couple of weeks ago in an accident in Peru, so he's no longer with us. But in that section, you'll find some perceptive articles by people who are dealing with the information flood. What will scholarly communication look like in the future? Will it be the traditional scientific paper? Will there be changes? And I'd like to convince you that there will be. And that, as Yasha said, this is available under a Creative Commons license, so you can download it, you can do what you like. If you want, you can buy it from Amazon for your Kindle, or you can actually get a bound copy on a print on demand. So, let me give some examples of what I mean by data-intensive science. Digital watersheds. So, in California, you can buy wine from the Russian River Valley. It's a small valley north of San Francisco. Now, over the last 100 years, there have been great changes. They've chopped trees down, they've planted crops, now they plant vines, they've built towns, built houses, they've drained the river, they've polluted the river with factories, they've mined the river for gravel. And what we're trying to now do is see what's a sustainable environment for that digital ecosystem. How can we keep so it's actually good for fish? If you look at this picture on the right, you'll see on this dam, they dam the river, of course, you'll see now there's a fish going up there. So fish have come back to the river. Can you keep it so fish can thrive in that ecosystem at the same time as allow people to produce wine, people to farm and to live in that area? And so these are the challenges. And this is a project we did with the Berkeley Water Center, and it illustrates the point about data. Because in order to find out the water in the river, you need to know the rain. And that's held by one agency called NOAA, the National Oceanographic and Atmospheric Agency in the US. They hold the precipitation data. But if you want to find out what's going on in the river, you will need the flow data, and that's held by a different government agency called the United States Geological Survey. So in order to put these together, you need to get data from one agency in one format, data from another agency, and put them together to make sense of what's going on in that valley. And so this is how you need data sets to be combined in order to understand what's going on in that ecosystem. So that's one example. Another example, which I think is encouraging from healthcare, autism, which is usually very intelligent children, are unable to relate emotionally and socially, and it's actually growing dramatically in the US at the moment. It's perhaps because of better diagnosis that people would like to understand. And so there are many organizations and funding agencies funding studies into autism. But they're typically rather small studies, and you have to worry about patient confidentiality, privacy, and all these things. So what is particularly heartening about this is that these agencies who did this funding have got together, and although their data is kept different places in different formats, they've agreed interoperability standards, this national database for autism research, where they can pool their data. So instead of having data on only a few thousand children, they now have data on over 80,000 subjects, and you can find out much more about the disease understand it better, you can do epidemiological studies much more easily when you have that vast amount of data. So again, that's putting data sets together, agreeing to interoperate, understanding what your interoperability standards are going to be. So that I find extremely encouraging that even in the medical field, they're managing to find ways to collaborate. If you want some more examples, we've just, on our website, we have, down here, Science at Microsoft, and we give some examples about how our computer scientists have been working with scientists to solve problems in healthcare and environment and genomics and so on. So you can find these on the web. Again, it's under a Creative Commons license. You can download it, and you're welcome to have a look at that. Supporting the data lifecycle. So, what do I mean by that? I mean that increasingly we have all these aspects of research, and central to that research is the data, and how we deal with it, how we handle it, what we do with it, and so on. So, I've caricatured, if you like, the phases of research from the data acquisition or the modeling on the computer. You may need to collaborate with other researchers, you may want to visualize the data, and then you want to do some detailed analysis in data mining to find out significant signals in that data, and finally you want to publish, share your results with the world, and so on. And at the end of the day, you spent a lot of money and time getting the data. You may want to keep some of that data. So for example, if you're measuring the temperature of the Black Sea, water and the salinity for the last 40 years, you want to be able to access that 20 years from now. And if you lose it, you've lost it forever because you can't go and repeat those measurements. Some measurements you can repeat. So for different fields, you decide what data you keep. Archiving and preservation is a real challenge, as we will see. So acquisition and modeling. So I talked about the new sensor networks being a source of data, so I thought I'd give one example. This is called the Ocean Observatory Initiative. It's funded by the US National Science Foundation. And actually outside Seattle, on the floor of the ocean, there's an earthquake plate there, so it's a very seismically active area. What they're doing is putting a fiber optic cable. And that will transform the way they do oceanographic science. Previously, to do data, you get on a ship, professor and 2 students, and they go out for 2 weeks, they take data, they go back to their labs, they take their tapes, their USB sticks, their data computers, and they spend the next few months analyzing the data. This completely changes it. 24 hours a day, 365 days a year, data will be streaming in from these sensor networks. And they can be very sophisticated things like a robotic thing you can move around on the seabed floor, or a video camera, or they could be just simple measurements like temperature and salinity. But now we will understand much, much more than we ever knew about the deep ocean on the floor of this seismic active area. So the field is going from being data poor, having very little data, to being flooded with data almost overnight. A second example, which we all know, we spent large amounts of dollars, $3 billion, and many years to sequence the first human genome. With the new throughput sequences, high throughput sequences, that we're now in several generations on, and it's now becoming very easy to sequence, all of us will be able to have our genome sequenced for less than $100 in a year or so's time. Maybe we'll go into the pharmacy and they'll do a quick test and say, well, for your cold, you don't need this drug, you need this drug. For example, it's a fact that 10% of people who take a drug called codeine in the USA don't respond to it. So you'd like to know from your genetic makeup if you're one of that 10%, and then get a different drug. So personalized medicine will come from all this flood of data. But the bottleneck now is not getting the data, the bottleneck is now managing and understanding what that data means. So large amounts of data are being generated. Collaboration and visualization. So we have these virtual communities. This is a virtual community too. Here we're meeting in person, but as we discussed, there will be virtual meetings too. For research you need that, and one of the things we're looking at is using a tool like SharePoint, for example, and we have now SharePoint in the cloud, to help scientists do the sort of things they need to do to collaborate, experiments, collaboration, archiving, dissemination, and then some administration and then some data mining. So this is a platform on which you can build specific tools. So we're working with a number of universities around the world, and they've been building special add-ons to this for their particular problem. So just to give two examples, the University of Delhi are looking at X-ray data, so they're doing a module for X-ray diffraction data here. And in the University of Oxford, they're looking at cancer images. So these are ways you can extend and tailor your virtual research environment to your specific problem. That's one example. Another more personalized example is, this is a tool not from Microsoft, it's a tool from academics in the US, called Mendeley, and it enables you to build up your own personal research environment. So you can find places to go and understand what the problem is, what the background papers, what the references you need to read. You can organize it, you can read and collect your thoughts, and you can collaborate and so on. So these are just examples of collaborative research environments that we will need in the future. Now, when we've got this data, there was a famous paper by Vannevar Bush, published in 1945 after the war, called As We May Think. And in 1945, he said, we're suffering from information overload. 1945. And no one person can understand all of science. He saw it fragmented. And so he had this vision, which has now become true, it's the hypertext of the web, that you'll be able to find the information you want by following trails of experts. These are these hyperlinks. And so we have these trails. What we need to do now is have similar trails through data. When we have complex data sets, in order to understand the conclusions, you need to follow an expert and to understand how they put the data together to come to a solution. So this is a tool we've developed in Microsoft Research, Worldwide Telescope. It's free, you can go and use it. And it gives you a view of the night sky as you've never seen it. First of all, you can see all the visible stars. But you can also, because this tool goes to the individual databases held by the astronomers, so they go to the infrared and radio waves, and you can look at the sky in the ultraviolet and X-ray and gamma rays, and you can look at the star formation, understanding what's happening in each of these wavelengths. And to understand star formation, for example, galaxy formation, you need to put all these together. So the reason I mention this tool is because it has the facility, just like I put together a PowerPoint deck, you can put together what he called a tour. Curtis Wong was the guy who developed this. Put together a tour where you have an expert. So here is one, Alyssa Goodman, she's an astronomer at Harvard University, and on this website you can see she talks about star formation. So she shows you data in one part of the galaxy, in the visible and the infrared, and then shows you how that's happening. She takes you on a tour through the data sets, showing how she comes to her conclusions. And you can develop your own tours. You don't have to do hers, but there are a number of tours of experts showing how they put their data together to get to a conclusion. And I think visualization tools like this are going to be increasingly important. I call it storytelling with data. I think that's going to be an important ingredient. So this Worldwide Telescope at the moment looks out at the sky. What's more interesting, I think, for most of us is looking at the Earth and understanding the Earth. So what we've been doing is using the same technology to look at the data for the Earth. And so this shows, it's called Layerscape, because there are various different types of data you can layer on top of each other to actually understand what's going on seismically in this area or in the ocean or whatever, and you can understand that. So it allows you to visualize, explore, and discover, and also you can build tours, just like you did of the astronomy, you can build tours through the data. So one example is this one. What's the seismic data taken each year and stored in a database, actually in Seattle, at the IRIS Data Center. And if you had this, for example, Wegener, who had this theory of continental drift, would have had no problem in convincing people. Here you see, this is the the Atlantic Ocean, and these are the seafloor spreading. These are the upwelling in the center of the ocean where the plates start spreading apart. On the left-hand side, you can see the west coast of South America, which is part of the ring of fire that goes round the Pacific. And so you can actually do tours of the data, you can understand the earthquake faults, and here you can see the tectonic plates immensely easily just by visualizing the data on a globe. And this is another type of tour. You can put a computer model. This is the Japanese Tohoku earthquake, and what you can do is you can look at each of these individual events. There was the big earthquake, there were shocks that happened beforehand, shocks that happened afterwards. They happened at different depths at different times, and you can replay the sequence. You can actually see where they happened, you can see when they happened. And this is a model of a tectonic plate going underneath the Pacific plate. So it's a subduction zone, which is a very dangerous thing because you can have sudden collapses which cause gigantic earthquakes and tsunamis. So here you can actually fly around your simulation, you can look at it, you can discuss it with your colleagues, you can show the features of that simulation to make them understand what's going on in that data. So those are some of the tools that I think you need to explore big data. These are just examples. I would just like to emphasize I'm talking about science, but actually I believe it also applies to the humanities and the social sciences. Increasingly, their data is digital. Already in social science, you have many data sets which are too large to store on your local computer. You have to get them remotely and put them together and combine them. And similarly, even in archaeology, although you have physical artifacts, you may want, when you're mapping out a site, to record the site digitally. So the amount of digital information, even in a field like archaeology, is becoming extremely large. And so, this is a tool done by Walter Alvarez. Walter Alvarez is a geologist at Berkeley. His father, Louis Alvarez, won the Nobel Prize in particle physics. And together they figured out the death of the dinosaurs. Now this is intrinsically a multidisciplinary activity. You need to know about dinosaurs, you need to know about geological history, you need to know about metallurgy. They discovered that there was this earthquake, this impact, meteor impact, from the layer of iridium that was deposited around the world. And they were able eventually to find out where this meteor had impacted in the Gulf of Mexico. And so what he was trying to do was be able to put all different types of data, geological timescales, historical timescales, biological timescales, cultural timescales, all together so you can make correlations that are difficult to make when you're looking at individual fields. This is a field that's now called Big History, and it's now being taught in several universities. So let me just give you an example, if I can get this to work. Find my mouse. So this is a prototype version of ChronoZoom. What it shows, it's a tool to explore big history. This is the galaxy. This goes from 13 billion years. This is the Big Bang down at this end here, and this is where we live, right at the end here. And you have all of human history and before the solar system, when the solar system was created. So I can take you on a tour of this. I can go, for example, and look in detail at the Big Bang. So that's down, it zooms down, and you see the first billion years. Go back out here, and we can look at the history of the Earth, when the Earth was formed. So we can go up here, and that's actually a relatively small part of history. And you can also look at human prehistory, which is even smaller. And so, if we want to find out where human history is, you see human history is a very small piece of this. And that's human civilization. On this timescale is tiny, and we of course live at a tiny sliver at the end of this thing. But by putting this together, you can look at huge timescales, you can put lots of information in there, you can compare and contrast. And so, just to finish, let's just go back. Then you see human history disappearing into the distance and eventually coming back to where we started. So that's an example of a tool that we think tools like that will be useful in the humanities. Analysis and data mining. So let me just give you a couple of examples here. Jim Gray's group, I used to have arguments with Jim Gray before I joined Microsoft, big debates and discussions about e-science and so on. And I thought I'd lost every argument with Jim, but when I joined Microsoft, I discovered he called his group the e-science research group. So that group now reports into me, and it's run by a senior scientist called David Heckerman, who is an expert in machine learning. He used to run Microsoft Research's machine learning group. We have about 100 or so people who are experts in machine learning in Microsoft Research. And so what they're now doing is using machine learning on these big challenges. And the hope is that we will actually understand and help the scientists solve some of these challenges, but also help improve our tools, which will then go into our products. And that's actually happening, and I'd like to just tell you a few of the things we've been doing. So, in the UK, we've been looking at diseases like asthma and diabetes and obesity, and trying to understand genetic and environmental causes. So we've been looking at very large data sets, and we've discovered some interesting correlations which are now published in places like Nature and so on. So by using machine learning, we can take some small steps to understanding these epidemics of obesity and diabetes that are now crossing the globe. In Brazil, we're doing a project on sugarcane. Sugarcane in Brazil, most of the cars in Brazil run on ethanol, not on gasoline. And what you'd like to do is to see if you can make an ethanol variant which is more efficient at producing ethanol. Or, for example, in global warming, temperatures will get hotter, and you may want to have a variety of sugarcane that will grow in hotter climates. And so those are the sort of things we hope to find out. At the moment, we're at a very basic stage. We're trying to sequence the chromosome of the whole genome, sorry, not just the chromosome, the whole genome of sugarcane. And so we're working with researchers in Brazil. And lastly, one of the scourges of the modern world is HIV/AIDS everywhere, as you know. And the problem with HIV/AIDS, the virus, it mutates very rapidly. So unlike influenza, which mutates, once a year we get a new flu shot, the HIV virus mutates in each of us who have it very rapidly, and so much more than influenza does in 20 years happens in a year in individuals. And it happens differently in different regions of the earth. And that makes it very difficult to have a vaccine that will be effective against it. So David Heckerman and his team have been working with researchers at Harvard and Oxford and South Africa to try and understand how you might design a vaccine that could be effective against HIV/AIDS. And the principle is really rather interesting. David Heckerman was the first person to use machine learning to develop a spam filter for your email. So how do you know it's spam? It may say it comes from my wife, but actually someone's been fooling around and it actually is not from my wife, it comes from a spammer. Or it may be that the machine's been infected by a botnet and we're sending me spam from someone else's machine. So what a spammer has to do, they want to sell you something and they want to get money from you. And those are the two things they have to make. Put all sorts of other stuff there, but they have to tell you what they're selling. Like they may disguise Viagra as B1 Agra or whatever it is, and they have to also money or to contact them. And so by actually finding out just these 2 points of weakness in an email, you can train a computer system to recognize that these are very likely emails. So with high probability, you can train it to say this email is probably spam, this email is fine. And so that's the technique they use for spam, and now they're using it for HIV virus. They're trying to find out points on the virus that actually the virus cannot mutate and change, so you train the immune system to attack this point. Normally it can just mutate in the next generation, it's not harmed by that vaccine. But now if you can train the vaccine to attack the HIV virus just at the right points, then you have a chance of actually succeeding. And that's what we're doing here. Actually, using data, getting data from different sources, the Open Data Protocol is an emerging standard. It's supported by Microsoft, by IBM, by SAP and others, and it's also now in an open standards body called OASIS. And it tries to use the simple standards of the web world as far as possible, XML and REST and so on, to enable you to get some understanding of the data. So over here is an example. We've been working with the UK Net Office to put weather data up in the cloud, and this is actually on the open government data site. We've now put the weather data from the Met Office in the UK up on that site. An Open Data Protocol can help you do that. Dissemination and sharing. This is a slide not from Jim Gray, but first arrived in Microsoft in 2005. This was a slide from a talk given by Bill Gates. And so he envisaged that the research paper we have now will change in many ways. So there's no reason, if it's not only on paper, if it's electronic, that you can actually go, they're doing an analysis of data, you can be able to go to the actual data. You can interact with the paper, you can go and see what data, or you can see what the model they've used. They've actually analyzed it using this particular model. You can go to the actual computer model. You can actually see what changed the view. You can look at it in different ways. You can do different analysis on it. And so there are various ways in which documents will be dynamic. Now, we usually talk about papers about citation impact. There are other ways of measuring impact, and so, you know, Amazon says, you know, people who bought this book also like this book, and that's how they recommend books to me. And you can have similar things. You know, this paper was liked by Jim Gray, this paper was liked by Tony Hay, or whatever, and you can choose what you like. So there are various ways of reputation and influence that the electronic world gives you that you don't have on the paper world. So research reporting is going to change dramatically. So let me just say now, I've talked about scientific papers, I've talked about going to the data. Increasingly in some fields, the data is all important, and there are people who spend their lives producing world-class data sets. In biology, for example, there are upwards of 1,000 public databases in genetics, which are maintained by individuals or by organizations, and actually they're built and cost a lot of effort to maintain. So there are a number of issues here. They have not only the data, but they have to have annotations and metadata telling you what data is there, what you can do with it, what you can't do with it. They often use other databases to get their annotations or to include in their database. But if you're spending a lot of time doing this, you're doing a very useful job for science. How do you get credit for that? It isn't a scientific paper in the traditional sense. So that's the problem the scientific field has. People who are data curators like this need to get credit. This is an essential part of science. How do we actually reward them? So those are some of the challenges. When you publish it, there's all sorts of issues. You've got to tie data together from different places. You've got to do the annotations, comments, observations. This is reliable, that's not, whatever. And where did the data come from? The provenance of the data. And there's the format you publish. And finally, you may, if you're in a collaboration, you may want some of your data to be public, but some of it to be private until you've analyzed it. And you need to worry about security and access and so on. And these are important issues. So those are some of the issues that I think information management in this age will have to deal with. One of the little projects that we're doing is producing an open source add-in for Excel, which you can use, which allows you to annotate an Excel spreadsheet. Data in an Excel spreadsheet contains lots of calculations behind the columns. How can you preserve that? How can you use the data there? People don't know what's there. Well, you can annotate it. But there are little issues about long-term preservation, because the software of the spreadsheet probably will be a new version in 10 years' time. The operating system may be a new version in 10 years' time, and the hardware on which this runs on will be different in 10 years' time. How do you actually preserve data in a spreadsheet? Interesting challenges for computer science. So this is an add-in. We're working with the NSF project called Data 1, which is their major project looking at data sets. in the environmental sciences, and with the California Digital Library. You want to give credit to the right person. Well, if you're from Korea, for example, there are many Professor Kims, and you'd like to give credit to the right Professor Kim who did this research. When I look myself up on Google Scholar, I find most of my papers there, but I find papers by Jeff Hay, who's a biologist. I'd like to make sure that they only have my papers. And similarly, you need to disambiguate, and so ORCID is an attempt to give a unique identifier to each researcher, which is persistent and you can be unambiguous as to who did the work. Similarly, with DataCite, it's an organization to give a persistent resource identifier to a data set. So you can refer to a data set rather than a website, and you'll be guaranteed that that's not going to go away to change and so on. There's a unique identifier. And this is part of the process, I believe, of giving people credit for publishing data. Archiving and preservation. At the end, you want to save some of this. This is something that's absolutely scaring researchers in the US. The National Science Foundation has suddenly said that actually for every grant proposal you put in, you have to have a data management plan. Now, most US scientists don't know what a data management plan is, and so they're having to learn very rapidly what's a data management plan, because it's going to be part of the review process if you want to win an award. In the UK, we set up an organisation in the eScience Initiative called the Data Curation Centre, Digital Curation Centre, which was an attempt to bring librarians with computer scientists, information managers, together with scientists to solve some of these problems. So on their website, you'll find all sorts of interesting things about data curation, digital preservation, but you'll also find some examples of data management plans. So if you want to write a data management plan, take an example from here and start from there would be my advice to my US colleagues. So lots of challenges in data. So what I would like to say then is about research libraries and repositories, which is related to the above, but different. So this is a slide from MIT. It shows the price of journals, that's the red line, going up over from 1986 to 2004, 20 years nearly. And the blue and purple lines are the consumer price index, the cost of living. And what you see from that is true all over the world in libraries, that the cost of journals in a library has gone up far faster than the cost of living. And library budgets have not increased at much more than 2 or 3%. And so when you have journal prices going up by large sums, 10% a year, there's a problem. There's a crisis in libraries in subscribing and paying for the library journals that the faculty want to use. So when I was Dean of Engineering, I was supposed to be told by my Vice Rector and the Rector to go and monitor the research output, make sure my faculty and students are doing that. But the university library was not able, because of the budget, to subscribe to all the journals that my staff published in. I had 200 staff and about 500 postdocs and grad students, and they published all over the place. So what we did was insist that we keep a digital copy of everything they produce for research. And we keep it in the repository. It was originally engineering faculty, now it's university-wide. My wife this afternoon will say some words about that. She was responsible for creating part of that. So we kept a digital copy, and that's, I think, essential for a research university to have a record of the research output of the staff. And just what do I mean by a digital copy? Most journals, over 80%, allow you to keep a pre-refereed version on your website. So you can put the pre-refereed version. When it's published, you can put either a link to the publisher, or you can, if it's delayed open access, that you can see it in 12 months or 6 months or whatever, you can do that too. But what you need to do is capture, first of all, the research output. And that, I believe, is the role for the research library. My students in engineering and science rarely went into the library for what we would regard as library purposes. They went there, a quiet place to work, to use the Wi-Fi, have a cup of coffee, meet their friends. In the US, you can do that in Starbucks. Why do you have an expensive library where people can access journals online? They don't need a physical building. What's the purpose of a library? What are the trained librarians going to do in the future? Well, I think they have a key role, and one of the roles is to be the guardian of the intellectual output of the university. And that's why I think research repositories are an important part of the university's reputation management. So, this is some facts, which I think I find interesting. This is from Virginia Tech. The Dean of Engineering there insisted that they have all their theses electronically on the web, and that was happened in 1997. And at that time, the number of accessors, requests for PDFs for these theses, was 200,000 per year. What absolutely amazes me is that 10 years later, that's now 20 million requests for theses. So it just shows you the power of making things available. People read your stuff, people know about what you're doing at your university, in your department, in research, if you make it available through the web, and findable and searchable. So I'd like to, there are many tables of rankings of universities, and when I was dean, I had to do rankings of my university in the UK. Your money you get for research depends on your ranking, so it really matters. This is one way of doing it. It's not the way they do it in the UK, but it actually is using what you, as your university, puts on your website, what you make available for the world to see about your university. So they have 4 different rankings. One, they have visibility, which is the number of external links coming to your site, so actually people like page rank, if you like. The other is size web pages, which seems to be not a particularly relevant thing, because you can make the website as big as you like. They then have what they call rich files. That's a number of research papers, PDFs, docs, and so on, up there. And just having the number is at least a part of it. But the Scholar Index, which is 15% of their total weight, is the number of papers that are cited, the citations that you get. And so you can look with Google Scholar, for example, and find the citations to these papers. And so that's what this organisation has done, and they produce rankings on that every 6 months, and this is their top 25 from July a year or so ago. And it's no surprise that you see in the top 25, all but one are US universities, and Harvard, MIT, Stanford, Berkeley, the usual suspects are at the top. The exception is the University of Cambridge at number 23. So that's one way of ranking universities. You can do that on a country basis, and you can do that in Turkey. And I looked at what they did in Turkey. I'm not telling you, go and look for yourself. You can find out where your university comes in this list. What I want to just draw your attention to is just the column labeled Scholar, because that is to do with your research. And your research, do people read and cite your papers? And if you claim to be an important research institution, people should be reading and citing your papers. If they're not, then it's difficult to argue that you're really having an impact. So this is just looking at the Scholar rankings, and here you see a different list. And it still has Harvard and MIT at the top, but it has some surprises. There's UNAM, that's in the University of Mexico. That's a small university, 200,000 students. So, you know, the largest university I've ever been to. And then some surprising ones. I will, of course, pick out the University of Southampton at 21 on this list. And that's because we've made our research visible to the rest of the world. And you can see that Southampton and Virginia Tech, I would say, are anomalously high. There's no way that they're better than, for example, Oxford and Cambridge. But at this particular moment in time, Oxford and Cambridge haven't got their papers visible to the world. And so they appear low on this. And this is something that anybody can do. People will do these things. This is your public data. So I do firmly believe that it's not a perfect metric, but it does tell you something about the research reputation of your university. And you can do something about it. you can make sure your papers are there. That's something you should be doing with your research library, making sure your staff and your students' papers are visible to the outside world and part of reputation management. So that, I think, is part of the future of libraries. Besides just the papers, as I've said, they will contain lots of other stuff. In the future, I think they will also contain data, so I think librarians will be helping scientists do something with their data. How do they curate their data? Librarians have skills that can help them. So data, images and software could also be there. And there are various different types of repositories. I'll just give two examples of a subject repository, which are centralized. There are other ones. I was talking last night about the one they have in France called HAL. But here I'll talk about the National Institutes of Health, National Library of Medicine and Archive, and then an organization called COOR. So, National Library of Medicine, you have Pubmed Central, which contains the papers, but then you can go from the papers to a number of databases, and you can actually go and search and find new results by using a wonderful tool they have called Entree, which does a cross-database search. So that's an example of where heavily curated data is linked to papers, and you can do all sorts of wonderful exploration. Another example is what physicists do. They put all their papers, they send them off to their favorite journal, but they put their electronic version, their e-print, on the web at a place called Archive. And every morning, every physicist will go to Archive to see what's new. And eventually, some of them are accepted, for example, for physical review letters. And it's like a stamp of approval. This is like post-publication review. So these are available to anybody, before refereeing, and then if they're reviewed, they get a stamp, this was published in PhysRev letters. Interesting model for other fields, perhaps. And then COOR is a coalition of open access repositories. It's trying to make sure that if you don't have a centralized place, we need to actually be able to combine the information in different university repositories. And I think it's an important thrust. And there is one university in Turkey that is a member of COOR. And again, I won't tell you that. You can go and find out for yourself on the website. But it is not this university. So, a few words on open data and open science. In 2003, funding agencies and research organizations met together in Berlin, and they were passionate that to solve the problems of the world, we needed to make scientific data openly available to as many people as possible. So you can benefit from research done in Australia, they can benefit from research done in Turkey, and to solve the problem of climate change, for example, or medical. And so I just wanted to point out that open access means not only papers, but scientific research results, raw data and metadata, and all sorts of other source materials. So it's getting the data available. And in the UK, the new government, not so new now, are committed to making the UK research data and publications available under an open access mandate. And they've just actually acted on this in the last year. So around the world, there are people acting and making data and publications available under an open access agreement. And I think that's extremely important for science. So this is the vision that, another slide from Jim Gray, and it's one that I subscribe to, that what we're trying to move to is a sort of pyramid where you have at the top open access papers, all the papers in the world on science will be available open access, so you can find things, you can understand what people have done. You won't have to repeat it because you didn't know somebody else had done it already. And then you'll have the data it depends on, the raw data, the data sets down the bottom. And then maybe you can combine your data with some of this other data to make a new discovery. And in that way, I believe, and Jim Gray certainly believes, that you can remove some of the inefficiencies of the way we do science. We do a lot of reinventing of other people's research. And if we knew about it better, if we could find it more easily, collaborate and so on, we could accelerate the way research is done and help solve some of the problems facing the world. So I think it's important. So lastly, just to finish up, I'll just say a few things about clouds, search and semantic computing.
So there's a lot of talk about clouds, and there are various ways you can do it. You can either rent clouds, computers in the cloud just for the hour, for a semester. David Patterson at Berkeley teaches parallel computing. So he has a class like this, and he gives all of you 1,000 computers to go play with. How does he do that? He rents them from Amazon in the cloud. And he does it only for the duration of his class. So he doesn't need to buy them permanently. He can rent them to teach parallel programming to the students. That's just one example. Other people may not be happy with the idea that someone else has been using this because it had my special data on, so they're worried about it. So you may have a private cloud or a dedicated cloud. There are different configurations. And many people call clouds all sorts of a data center, a computer center as a cloud. What Microsoft means by a cloud is this. So we have these very big data centers around the world which have these large containers. And these containers contain several thousand servers, and they're configured and designed to be very energy efficient. And you put them next to a power plant where you can get cheap energy, and it's a very cost-effective way of running servers. So this is what Microsoft means, and we have these around the world. In Europe, we have them in Ireland and in the Netherlands, and we have caching centers, if you like, in other places to make sure you can get the data. If you're not in one of those countries, you can get them very easily. And so we've been exploring, and this is a European project we did, virtual multidisciplinary environments using cloud infrastructures. And what it looked at was a whole range of different types of problems. So I'm not going to go into them, but people are using the cloud to find out what's the cloud good for, what's it not good for, is it good for curating data, for preservation, and so on. So we need to understand the cost of putting data in the cloud, the cost of keeping it there, the cost of accessing it, and you need to see what's the best solution for your university, for your research institution. But I think it's certainly a very exciting development and will be part of a future IT infrastructure. The other thing I'd like to talk about is academic search. I talked about finding research papers. Microsoft Research in Asia have been working on a tool called Academic Search here, and what they have tried to do is get as many papers as possible accessed and indexed in this search engine. We've certainly done it well for computer science, and we're now trying to do it for other fields. We're working with publishers to actually get their data. So it's certainly not ready, finished product at the moment, but it's a beta. But it allows you to search for papers, see details of conferences, organizations. You can find relationships between authors. I would suggest you go and have a look at it and see if it has the sort of things you want. If it doesn't, you should let us know, because it's still a research project. But for example, I can look at, on citation count, what are the top 10 computer organizations in the world for computer science? Well, if I look at this here, over the last 5 years, there's Microsoft Research, Stanford, MIT, and so on. I've chosen the last 5 years because if I chose 10 years, Microsoft Research would not be top. So if you want to display your organization to the best, you can choose how you display it. So you can choose what criteria you want to show and boast about your organization. So this is just one example on simple citations. But actually, it's important because what our tool does, it offers you an API. You can use the data you've got to build your own tool. You don't have to have webometrics, you don't have to have a citation count, you can use your own. And there's this API which allows you to do that. And this is an organization at the University of Washington. It's a small group in biology, in fact, who are doing just that. They're taking our data and producing new tools to show different mappings. So, for example, the ranking is not just a citation count, it's like a page rank count. It tries to count other things other than just citations. And they have also wonderful diagrams. This is a diagram showing the multidisciplinarity of papers published in Nature. So Nature's down at the bottom here, and these are all where the references are to science, to the proceedings of the National Academy of Sciences and so on. This shows you the multidisciplinarity of papers in Nature. So you can do those yourself, and this is another organization, Altmetrics, which is not only looking at citations and scientific papers, but also blogs and Twitter and everything else, trying to measure the total impact of
your research. So those are just examples. So I should conclude, and let me say a word about semantic computing. We know computers are really good things for doing computing, right? And they can do data storage, and they can manage lots of data, and Microsoft and Google index the entire web regularly. So they're very good at doing that. But you heard about how many books are published each year and how few we need. I talked about the National Library of Medicine. Every minute of the day, 2 papers are deposited in their Pubmed database. 2 papers every minute of every day of the year. Now that's a huge number of papers that nobody can keep up with. So we need help in that. And so we need to have ways that the computer can actually help us. If it goes to a website, it has no idea what the website contains, whether it's astronomy data or whether it's restaurant data. It just knows the name of the website, and so and some keywords at that website. So can we help them by giving them some machine-readable information? So we need them to help with acquisition, aggregation, correlation, interpretation, discovery, organization, analysis, inference of all this knowledge out there. And so it's just beginning. An example is this add-in for Word, which is semantic chemistry. If I type in CH4, because I've used chemical markup language, the computer understands the capital C as a carbon atom and the H as a hydrogens. And it gives me the choice of either do you want to call that methane, or do you want the chemical structure, or whatever. And so that's the beginning of chemoinformatics. Similarly, this is when we have medical images. A doctor can immediately tell that's a heart, that's a liver, that's a kidney. Can, for example, a computer detect from this image what the artery is? And so that's what we've been working, trying to get semantic understanding of images that doctors can immediately see. Can we help them by having a computer be able to recognize individual organs in a body? And that's a major challenge for computer science. And this is another object. When you store data in your repository, what you'd like to know is that this paper is about a particular, for example, this paper X is about star Y. You can put these little triples of information in there, and that's what this enables you to do. It's called Zentity. It's an open source thing we've developed at Microsoft Research, and it's used by universities and various places to actually put some semantic information into the database. So I think those are beginnings, but I think machine learning has a lot to offer. I think Tim Berners-Lee's ontologies and so on will also be important. But what I think is quite clear that, last thing, this is that the only thing I think Microsoft and Google have agreed on with Yahoo, it's a vocabulary for helping computers understand what a website contains. If I'm looking for Casablanca movie with Humphrey Bogart, or Casablanca is a place in North Africa, but if you could put little microdata in your website and say this site is about movies, this site's about North Africa, the computer could figure out that site's not relevant to my search, this site is, because it knows I'm looking for movies. And so that's what this is about. It's about a vocabulary, and actually people can extend that. So it's a small step to semantic web, if you like. And so in the future, I think you'll have resources you keep locally at your desk, on your laptop, or your tablet, or whatever you carry around with you, and also you'll have resources in the cloud. You'll have identity services, you'll have data services, you'll have compute services, and possibly visualization services and curation services. So there'll be a mix of things, and I think what you need to decide is exactly what mix you need for your particular problem. But this is where I think we're going, and I think it's a wonderful opportunity for departments like the Department of Information Management to make real contributions to helping build these intelligent services of finding, going from data to information to knowledge, information we can act on. Thank you very much for listening. I apologize for going on 5 minutes.
Doktor Tony'ye bu büyüleyici ve ufuk açıcı konuşması için çok teşekkür ediyoruz. Eğer birkaç sorunuz varsa sanıyorum ki kendisi sorularınızı cevaplayacaktır. Peki Bey, alanda mikrofon gezdiriyoruz sanıyorum. 3. sıraya gelir misiniz lütfen?
Anlattıklarınız çok etkileyiciydi. Çok güzel. Hocam ben ufak gerekirmişim.
Can you translate? Sorry, that. I made it French, Spanish, and Italian, but I gave up on Turkish.
Anlattıklarınız çok etkileyiciydi. Gerçekten bir aydınlanma yaşadım ben kendi adıma bugün. Şu anda Türkiye'deki genel durumu da analiz etmiş görüyorsunuz. En önemli başlamamız gereken, yapmamız gereken nedir? Özellikle açık erişim konusunda. Bize ne önerirsiniz? Nereden başlamalıyız?
Okay, so thank you for the question. And I think really it depends who you are. I think that funding agencies should look at what's happening around the world, and I think, for example, Turkey would clearly benefit if open access happens in other places. You will be able to access other people's research, and the US, for example, is very open about its research, and they will also have an open access. National Library of Medicine already is open access. So I think having a reciprocal arrangement where research funded by the government of Turkey is actually made available to the public and so the public can see, I think, would be beneficial. That's one message. For the universities, there are several things. One is, I do believe that research repositories are important for you to highlight the contributions made by Turkish researchers. So people know about what you've been doing, people cite your papers, and you can actually play a part in the international community solving problems people care about. So I think to universities, and for example to the Vice-Rector, I would put as a very high priority making sure you have an open access research repository in your university, and your library is moving to understand that its major role to be the centre of the university is to support the research outputs of the university. So, as you can tell, I feel passionately about that, nothing to do with Microsoft. But I think then the research agenda is to find the tools and technologies, and I think there's a wonderful opportunity now for IT, computer science departments, information management, and so on, to come together to create tools that people want. And I think there's no reason why tools that are created by this university or this community actually can't be widely used and successful around the world. That's what actually the web allows you to do. So I think you can have real influence and you can make some things that are important for Turkey, but also important for solving some of our problems. So I think it's an opportunity. I really do.
Thank you very much.
Tekin Bey, çok teşekkür ederim sorusu için. Bu arada ben de burada bir duyuru yapmak istiyorum izninizle, konu açık erişime geldiği için. 8-9 Kasım 2012 tarihlerinde Medoinet ve OpenAIR Avrupa Birliği destekli projelerinin ulusal açık erişim çalıştayı var. Ankara'da yapılacak. Bunu da bu vesileyle sizlere duyurmuş olayım. Daha sonra kuşkusuz bununla ilgili duyurular alacaksınız. Son bir soru alalım. Zamanımızı aştık. Var mı başka sorusu olan? Arkada görüyorum. Bir soru daha alalım.
If it's okay, I'd like to ask my question in English. I think one of the interesting things about e-science is it brings together different disciplinaries, and the world is more shifted towards more multidisciplinary environments, which is a really great opportunity because it gives us a different perspective from different standpoints. And from what I understood from your interesting presentation is that the university is also dematerializing and decentralizing, not just the publishing. And so in that respect, how would you see the future of the university itself? Because you're not also talking about the walls and the campuses. The university is also kind of expanding. And also in a world where university education is becoming more expensive. And at the same time we talk about the freedom of information. But on the other hand, the university tuition fees kind of increasing, which is the case in the UK, for example. So
also in the US.
Yeah. So I think this is a challenge, and I'd like to know what would you see on that.
Thanks. So thank you for the question, and it's a difficult one, obviously. I spent my life in university trying to do multidisciplinary things, and it's not so easy because the money comes in labeled physics, chemistry, maths, and actually making people actually work together and give away money is how they see it. That's why I think it needs to come from the top of the university that they actually insist that some of the money is actually for multidisciplinary activities. So I think that's important, and you're right, just as we see this campus is only one of the campuses of the university. There are 2 other campuses, and actually you need to connect people together, and technologies can help do that. I happen to believe there's no substitute for personal contact and personal collaboration, but it needs to be supplemented by a virtual collaborative infrastructure. And with high bandwidth internet connections, which you have now in Turkey, I think you can make those things happen. The education thing is important. I happen to believe that universities are extremely important, and that education is really the only hope for humanity, right? So I happen to believe that universities play a vital role, and enabling people to do that and having the tools and technologies so that they learn and understand is a critical challenge for universities. In the US, there's great excitement now about these things called MOOCs, massively open online courses, where at Stanford they did an experiment. They had it was an artificial intelligence graduate course, and they made it free to anybody over the internet. And they had 100,000 students, and 30,000 finished the course. So that's a remarkable thing. If you just taught it at Stanford, you may have 30 students finish the course. So that's a real game changer, potentially. I don't know quite how you make that work financially, because it costs people money to do that. Also, I don't quite know what it means for other universities. If you can hear a Turing Award winner lecture on artificial intelligence, why would you want to listen to Tony Hay on artificial intelligence? You may as well go listen. So I think there are challenges, but I do think there's no substitute for face-to-face interactions. And so one of the concepts of these massively open courses is the concept of the flipped classroom. Instead of sitting in an audience listening to me for 50 minutes or whatever, you have lectures which are in chunks which are smaller than that, which you can hear in your own time, and you use the time together to interact and do problems, to do different things. You use the time differently. And so I think those are all elements. But no, I think it's a real challenge. And can we use our technologies to make education easier? Surely we can, but people are different. People learn in different ways. And so, for me, having tried to use technology for the last 20 years in education, I don't know what the right thing to do is. After 20 years as an academic, I have no idea how best to use it. But it's exciting and important.
Çok teşekkür ederiz. Zamanımızı biraz açtık ama eminim çay arasında Sayın Tony Hay'e sorularınızı yöneltebilirsiniz. Oturuma ara vermeden önce bir sonraki oturumda Türkiye'de altyapılar ve e-bilim konusunda bir açış konuşmacımız olacak. Ben Sayın Tony Hay'e tekrar teşekkür ediyor ve Sayın Rektör Yardımcımız Profesör Doktor Ali Çağlar'ın kendisine sunacağımız armağanı vermesini arz ediyoruz.
Thank you very much. Now I have to get
back to America. Thank you very much.
Peki, şimdi çay anlatmak için